The next invited talk will be given by Professor Oren Kurland from the Technion. He's very famous in the field of information retrieval. Has several awards from, right? Also from Yahoo.
From Yahoo.
Yeah.
Thanks to you.
Google, Yahoo, and IBM.
Okay. So first of all, I would like to thank the organizers for inviting me here. It's always a pleasure to come here. The work I'm going to tell you about was done with my PhD student Fiona Reiber, and it was presented in CGIAR last year. And I should mention that the work was done part of the Electronic Commerce Center at the Technion, which is a joint Microsoft Technion center. Now, what I'm going to tell you about is search, and I'm often being asked, why am I doing work on search if Google and Bing have already solved all search problems? And I do like this anecdotal example, which will enable me to actually bring up two open challenges in information retrieval. So probably most of you know the DBLP repository of scientific papers. I went to two major web search engines and typed in my name, my first name, my last name, and DBLP. And I won't tell you which search engine is which, but let's look at the results which were obtained by the first one. So the first result which I got here is actually for a guy named Michael Bendersky. He was my first graduate student at the Technion. Currently he's with Google. David Carmel is a researcher with IBM Haifa, with whom I've, oh sorry, he moved to Yahoo, and we keep collaborating till this day, yeah. Now, the most interesting result is the third one. I don't know this guy. We have never published a paper in the same conference or journal, and till this day, I haven't managed to make any connection between him and myself. So I would say that the results here are not that great. On the other hand, when I went to the second search engine, I did find my record, my DBLP record, as the first result, which was great. Liron was also a grad student of mine about 6 years ago, and down the road the results get worse. So here is an anecdotal example for why I am working on search, specifically ad hoc retrieval. But this example actually brings about two very interesting problems which I also work on, but I won't discuss today, and which are actually open challenges in information retrieval. The first one is, how can a search engine predict whether the search is going to be successful? Because if I were able to design such an algorithm for prediction, I would have been able to actually send my query to the right search engine. Second of all, if I were to predict the search quality, I could have potentially merged the two lists, which is the rank aggregation problem, using weighted combination. So these are two open challenges in information retrieval, which I want to discuss today. I will discuss the fundamental task, ranking documents in a corpus by the relevance to the information need expressed by a given query. Now, for those of you who are not familiar with retrieval approaches, here is information retrieval 101. Say that I got a query Technion. I can represent it as a vector and write 1 in the component that corresponds to the Technion term. I get a document which I want to evaluate its relevance with respect to the query, and I also represent it as a vector. And here I have 2 because I have 2 appearances of the term Technion. Now, once I represented my query and document as vectors in a vector space, I can say use the cosine measure to evaluate the similarity between the document and the query, and I can use a variety of term weighting schemes. This was first published by Gerard Salton in '68. By the way, it's not the first retrieval framework. The first one was the probabilistic one. So this is a very simple approach to ranking documents with respect to queries. And a previous speaker has already mentioned that around '98 there was quite a revolution in the world of search engines, and Alta Vista was mentioned. And nowadays, when we look at web search engines, they use tons of relevance signals so as to estimate whether a specific web page is relevant to a specific query. Some of the signals could be query dependent, for example, the textual similarity between the page and the query. Some could be query independent, for example, the PageRank score of the page, which attests to the prior probability of the page being relevant to any query. Now, what do you do with all these relevant signals? And there are actually thousands of these. You can use a training set wherein you have queries and pages which were marked as relevant or non-relevant to the queries, and use a machine learning approach to train a ranking function. So as, for example, to assign weights that reflect the relative importance of each of these signals. And this is the current state of affairs with web search engines. Now, what I would like to focus on is the simple feature, which is the document query similarity. First of, and why do I want to do that, except for writing papers, of course? The first reason is that when we come to estimate relevance, we should answer the basic question of whether the content on the page satisfies the information need that the query expresses. And this is the ultimate test for relevance. So this signal touches on the most basic question we are trying to address. The second thing is that many studies have shown that regardless of all other relevant signals, the document query similarity is still one of the most important relevant signals for ranking documents with respect to queries. So the question is whether we are back to classical information retrieval stuff. So I'm going back to classical information retrieval stuff, and I'm revisiting the cluster hypothesis, which was first stated in 1971 by Nick Jardine and Keith van Rijsbergen. And here is the statement. Closely associated documents tend to be relevant to the same requests. Naturally, in order to instantiate the hypothesis, I need to quantify associated. And I will do that in a few seconds. The operational consequence of the hypothesis, or at least one of them, is that relevant documents should be similar to each other and should be more similar to each other than they are to non-relevant documents. And then the question is, if I were to devise a similarity metric for documents, say you represent them as vectors in a vector space, or you represent them as language models in the simplex, how do you use the operational consequence in order to devise a retrieval algorithm? So what happened after the hypothesis was stated at the beginning of the 70s, people have started using clusters of similar documents to improve search effectiveness. One of the trajectories that was pursued is the following. People have tried to actually visualize results using clusters. So there is a web search engine called clusty.com, which you can go to and type in your query. My query here was Technion. On the right-hand side of the results, you get the linear list of results which we are all used to. On the left-hand side, we get a tree of clusters which were created from the linear list which appears on the right-hand side. Now, how does it work? Clusty targets the query to some search engine and gets the top 1,000 results. It uses the snippets, these short summaries of the results, so as to cluster the results. Then a clustering algorithm, specifically here an hierarchical one, is being applied up on the 1,000 results. The clusters are automatically labeled using any algorithm which you would like, and there is a lot of literature about automatically labeling document clusters, and that's it. Now, till this day, nobody has managed to show that using such a cluster-based interface results in more effective retrieval than using the standard linear list. And one of the main issues in making this interface actually be more effective than the standard one is the user browsing paradigm. Namely, what order should the user use in order to traverse the clustering tree? In other words, how should the system order the clusters relatively to each other so that if we use a linear traversal paradigm over the clusters, we will get a more effective retrieval than one which is being applied here. In other words, the challenge becomes finding the best clusters here on the left in a completely automatic manner. Now the question is, why should we bother? Why should we bother to do all this quite expensive process create the clusters if we are not guaranteed that there is some merit in doing that. So let me wait a second with answering this question and present you with an alternative to using cluster-based interfaces. We can actually use clusters of similar documents without letting the user know that we are doing that. In other words, we can use in the background a mechanism, specifically a retrieval mechanism, which depends on clusters, but the user doesn't know anything about it. And here is the way it works. And this chain is often called in the literature cluster-based document retrieval. You take your query and you use some search engine to retrieve an initial list of results. You take the top results and cluster them using whatever clustering algorithm you would like to use. Once you have a set of clusters, you rank the clusters. Once you have a ranking over clusters, you use a function so as to transform it to a ranking over documents. Now, this final step of transforming cluster ranking into document ranking is quite trivial. You just go over the list and decompose each cluster into its constituent documents. The tricky part of this process is this one. How do we rank clusters of documents? And in essence, we had hard time addressing the question of ranking documents, and instead of addressing the question, we actually came up with a new question, which is how can we rank clusters of documents? Now, I should justify why we should use such a retrieval process. We start with a query, initial set of documents using a standard search engine. We go through a clustering phase so as to re-rank the top results from the initial search, and we end up with a ranking of documents which should presumably be better than the initial ranking that we had. But what guarantee do I have that this step of ranking clusters will result in improved ranking of documents? So here are some numbers which exemplify the huge potential in using this cluster-based retrieval process. This is a standard retrieval approach from the literature. This is a highly optimized retrieval approach which is based on the principle called automatic query expansion. Since queries are usually short, one of the most effective approaches to handling issues that rise due to the short length of queries is automatically expanding them. So these are the results, the performance results attained by using such an optimized automatic query expansion approach. All numbers are the precision at 5, which means what percentage of the top 5 results are relevant to the query. Now say that I were to apply this chain, and here instead of applying an algorithm, I were to go and manually compute the percentage of relevant documents in each cluster, and say that I picked up the cluster with the highest percentage of relevant documents and just presented its documents as the final result. These were the performance numbers which I would have attained. As you can see, the gaps are enormous. There is no current retrieval system reported in the scientific literature that can get for these 3 benchmarks such high numbers. The highest numbers you would see in the scientific literature would be around 60% precision at 5. This means that if we are to devise effective cluster ranking methods, there is a huge potential for such approaches. And this was the motivation for the work I'm going to tell you about. So we are facing a cluster ranking challenge. And in probabilistic terms, we want to estimate the probability that cluster C is relevant to query Q, which we can use the joint probability because the query is fixed and we rank the clusters with respect to a fixed query. What we did in this work was we estimated the joint probability using Markov random fields. Now, not getting too much into technical details, I will just tell you that Markov random fields are undirected graphical models which enable to infer joint distributions because of the Markov property. And what you do in these cases, you define a graph wherein vertices represent random variables and edges represent dependencies between these random variables. And the nice thing about Markov random fields is that you can factor the joint distribution by looking at the clicks in the graph. And these are potential functions defined over the clicks in the graph, and you need to define the potential functions. If you instantiate the potential functions as is standard practice using some feature function, the exponent of weighted feature functions, what you simply get is a ranking method for clusters, which is a linear in features. What we need to do here is to define the set of clicks in the graph and to assign feature weights to these clicks and to learn the weights. So let me just go quickly through the graph structure, specifically the clicks in the graph, so as to show you which kind of feature functions we have been using. The first type of a click is a click composed of two vertices. The first one is the query, and the second one is a document within the cluster, and this touches on the similarity between a single document and the query. The second type of a click is one which contains both the query and all documents within the cluster, and these feature functions which we have defined here are based on looking at the variance, the maximal and minimal similarities between the query and the documents in the cluster. The first type of a click is one which contains only the documents in the cluster, but which doesn't contain the query itself. This is a query independent prior for the cluster, which is based on properties of the documents, which might attest to the relevance of the cluster as a whole. Here we have used the PageRank scores of documents within the cluster, the entropy of the term distribution of the documents, etc., etc. So when you use all these feature functions, you plug them here, and the goal is to learn the lambda weights. This is essentially a learning to rank problem for document clusters rather than for individual documents. And we have used here SVM rank, which is the support vector machines version for ranking. And here is the empirical evaluation that we have performed. We took a query and we ran it into a highly effective search engine, and we retrieved the top 50 documents. We have applied very naive nearest neighbor clustering algorithm on top of these 50 documents, and we have then operated our MRF-based cluster ranking method that I've shown you. Once we got a ranking over clusters, we transformed it to a ranking over documents, and the question is, what is the resultant effectiveness of the search we got? So again, you have a query, you send it to some search engine for an initial search of results, you cluster the top 50 results that you got from the search engine, you rank these clusters, and once you got a ranking over the clusters, you transform it to a ranking over the documents, which simply means that we have re-ranked the top 50 results of the search engine using cluster-based information. The user, again, it's important to emphasize, the user needn't know that we have applied a cluster-based approach. This is all happening behind the scene. We start with 50 documents, we end up with 50 documents, but this version is a re-ranked version of the initial ranking. The question is whether we managed, via the cluster ranking mechanism, to improve the performance in terms of effectiveness over the initial ranking that we got from the search engine. And as I've already said, the search engine which we have used in the first step is considered to be a highly effective one. So here are the empirical results. These are two benchmarks. This one contains 23 million documents from the .gov domain. This one contains 50 million documents from a general web crawl. The red bars represent the effectiveness measured using a metric called mean average precision, and the purple bars represent the performance that we get using the cluster-based approach. As you can see, quite major differences, and the black marks represent statistically significant difference. Another question is, how do we compare with previously proposed cluster ranking approaches? So on over Gov2, we beat them all in a statistically significant manner. Here we beat 12 out of the 3 in a statistically significant manner. Another long-running debate in the information retrieval community throughout the years, actually as from the beginning of the 80s, was whether it is worthwhile to use document clusters, which is as an emphasis on the document side, or whether we should use automatic query expansion, which has emphasis on the query side. Up until 2 years ago, the answer was we should use automatic query expansion. And these results show that this is not the correct answer to provide to the question. So the red bars represent the performance of a highly effective automatic query expansion. The purple bars represent the performance of using our cluster-based paradigm. And as you can see, these differences are quite huge. Now, one other criticism about using document clusters for retrieval is that you will show the user documents which are very similar to each other, and the user is actually interested in a diversified result list. Say that you were to type in the query, the overused example in IR, which is the query Jaguar, you would have expected results which are either on the Jaguar cat or Jaguar car interleaved with one another on the page, because the query to begin with was ambiguous. It's not a clear cut what the underlying information need is. So to answer the question of whether cluster-based retrieval actually hurts the diversification of results, we did the following trick. We took the most effective methods from the literature which look into diversifying search results, and all of these are actually depend on 2 different components. The first one is estimating the relevance of a document to the query, and the second one is ensuring diversity. What we did with our cluster-based approach, we just replaced this component with the cluster-based retrieval method, and we got huge improvement also in the resultant diversification of the list. So cluster-based retrieval can indeed help to improve the effectiveness of search, both in terms of relevance and in terms of diversification. Let me just mention the following fact. There is an annual TREC conference, the Text Retrieval Conference, wherein research teams from throughout the world try to compete with their new search algorithms on newly published benchmarks. We have used the algorithm I showed you last year in TREC and came up first with respect to most evaluation metrics, and we did that using as an initial search. For the initial search, a highly effective learning to rank approach, which we re-ranked its results using the cluster-based approach I've shown you. To summarize, a new cluster-based retrieval paradigm, well, the paradigm is not the paradigm is not novel. What the novel part is the component of ranking clusters. And using this MRF-based approach, Markov random field-based approach for ranking clusters, showed much merit in terms of the result and effectiveness. And now we can surely say that not only is cluster-based retrieval very effective, but it's also more effective than automatic query expansion, at least those methods in the literature which are considered state-of-the-art. And finally, it does help to improve overall diversification of search results for ambiguous queries. Thank you very much.
Time for one question.
May I ask you?
As far as I'm concerned, you can ask 5.
Did you try to combine automatic query and cluster?
Yes, it doesn't bring merit on top of each.
Okay. Can you elaborate a little bit about mean average, the way you measure?
Yeah, mean average precision is a standard metric for evaluating the effectiveness of search results. You get a list of documents with respect to a query, and you have a label for each document, whether it's relevant or not. These are binary relevance judgments. So you get actually an order list of zeros and ones. Ones for relevant, zeros for non-relevant. And you need to come up with a single number which represents the relative ordering. Average precision, M is for mean, so it's mean average precision. Average precision for a single query means that the higher the value is, the more ones you have at the top ranks of the list. And in general, the more ones you have in total. So it's a very simple measure for how well you retrieve relevant documents with respect to how many of them do you retrieve from the collection and how highly are they ranked in the list that you present to the user.
Thank you very much.